Guys, let's get started. All right. We got a full day ahead, so let's get started. All right, so yesterday we did a lot of stuff in Jana, and at the end, we got the results of our analysis into a T tree, and so we're going to start talking about how you can analyze that in root. So first of all, the tree file for this session is located here. I guess instead of $workshop data, if you're using the public build, it's just dollar data in this path. But this is the T tree we're going to be using. So from before, when we were looking at a smaller subset of the simulated data, but now we're going to be looking at the first 50 files from the simulation. Before it was just the first 10, so we've got about five times the data this time than we had yesterday. And to remind you, when making this T tree, we didn't do all the cuts I showed you yesterday. We didn't do particle ID cuts. We just had a loose cut. We made sure there was enough tracks and enough showers. And then we did a loose cut on the pi0 peak, the omega peak, the missing mass squared, and required that the kinematic fit converged. All right, so let's talk about the data that's in the tree. It's called this part. The data is in this format called the part format, which is physics analysis root T tree. And the basic idea is there's one T tree entry per event, and so each tree entry is going to contain basic event info like the run number, the event number, and some metadata about what your channel was. It'll contain the thrown beam and the thrown final state particles if you were analyzing Monte Carlo data. And then it will include particles. It won't list all the beam particles, like all 80 to 100 of them. It'll only save the ones that happen to be in your particle combinations. It will save all charged hypotheses, all neutral hypotheses, and all particle combos. Okay, so what's a charged hypothesis? The idea is for each physical track in the detector, it could have several masses, one of several masses. Like it could be, if you have a positively charged track, it could be a pi plus, it could be a k plus, it could be a proton, it could be something else. So what the track reconstruction does is it's run for positively charged tracks for each of those masses. So for each positively charged track, you end up with 3 tracking results, or 3 hypotheses. So that's what those are. So if you had 5 positively charged track, you would have 15 of these objects in the event. And for negatives, it's pi minuses and k minuses. And then for neutrals, it makes hypothesis based on whether it was a photon or a neutron. So you have a physical shower, but the 4 vector that you get for the momentum is constructed as if it was a photon or a neutron. And then all the information on the surviving particle combos is there. And now most of this data is stored in arrays. For example, all the charged particles, all their, the measured floor momentum is stored in an array called this. So if you had 10 hypotheses, then this is an array of length 10. And there's documentation here detailing what it's like. All right, so let's open the tree in the browser and just take a look at it. So we've opened it up, and then the easiest way to do that is to go to the Scratch folder, because I have a link to the tree there. And again, if you're on the public build, you don't have a link, but it's in dollar data session 3. All right, so let's look at the tree. Start root. Open the browser. All right, so run number, this is simulated data, is all run number 10,000. All right, so nothing so exciting. Here you can see the PID of the thrown beam is 22 for photons. The P4 of the thrown beam, you can look at the Z, and this shows you what was thrown for the beam photons for the events that we recorded, etc. Scroll down a bit. This is the number of beam particles that were saved. So usually only one beam particles per event survived all those cuts. Sometimes 2, sometimes 3. And then you see some arrays for neutral hypo. This is the neutral hypothesis. No, not that one. So it's either the particle ID is either for photon or neutron. Beta for the timing. Ooh, let's not look at that one. Energy in the B cal, energy in the F cal. You get the idea, right? So it's same arrays, but for charged hypotheses, you get chi-squared. Timing, it's way out there. DDX in the top, etc. All right, so then you start getting into some combo information. For example, here is the form momentum of the proton that was kinematically fit. Kinematic fit PZ for the proton. So although this array holds all of the 4 vectors for the proton in all of the combinations, and there may be many combinations per event. Let's see, there are a lot of times there's only one combination per event. Sometimes there's 20. So it's a long array, but it's kind of so. This format does save everything in a compact format, but if you want to match the proton in a combination, which only has P4 kinfit, for example, back to the array back here, which has the measured form momentum here, it can be kind of a mess going through and handling it. So we've made software to make this easier to associate the information together. So that's where tree selectors come in. So if you're familiar with T-selectors, the idea is a root will generate a class to make it easier for you to loop over the branches in your tree and do data analysis. So it's still a little annoying to use. The root solution, it hard codes like the sizes of the arrays. So if your tree ever gets bigger, your array might be too small. It's kind of a pain to work with. I don't want to go into the details, but so that's why I've developed this root deselector, which is GlueX specific, and it makes life much easier. So first of all, it inherits from T-selector. So anything that you were using the T-selector for, this will also work, such as proof. But also, it solves some of these problems with the T-selectors. So like with the fixed array sizes, it's much easier to use with proof. You don't have to move code around, etc. And also, what this does is it provides a C++ interface to the data in the tree. So instead of working with individual branches, you have classes you can work with. You can pass these classes around to various parts of code, and it's easier to use. And the classes have names that are identical to those in Jana. So we didn't talk much about those, but if you know your way around Jana, it's very similar. And these classes just wrap around the content that's in the tree. So these classes aren't stored in the tree, but it's just an interface to the data in the tree itself. And the deselector, because the metadata for your channel was saved in the tree, it has knowledge of your analysis. So we can generate code to analyze your channel that's based on your channel. So there will be example code in there that we can look at that already histograms some useful things. So to make this deselector stored in a new GitHub repository here, and there's documentation here. So then what we can do is we can make a deselector using this command, make deselector, and you can run it with no arguments for instructions. And so again, I'm going to generate all the code live from scratch, and because this is being recorded, you don't necessarily have to type to keep up. You can look at the recordings later. And for reference, the final result from this should be is the selector stored here. And this shows us how to run. So, okay, so let's do this.
So you were mentioning the reaction-driven code generation.
Yes.
That is the step make deselector?
Yeah, that will do that. That will make a selector, your custom selector, which inherits from deselector, which inherits from tselector, but it will have code in there that's custom for your channel. So okay, let's take a look. Let's go back to here. Quit. Okay, and then. All right, so there's my. Let's run make deselector with no arguments. All right, and this tells me how to do it. So the first argument needs to be the input root ttree file name. So that's this guy. Actually. But the second one needs to be the name of the tree. And since I don't remember what that is, I'll do an ls. There's the name of the tree. Okay, so make deselector, the name of the file, the name of the tree, and then a name for our selector. I'm going to call it session 3A. All right, so we generated some files, and let's take a look at them. Ooh. Let me do that again, but with the ampersand. Okay. All right. So there's basically 3 main methods. Init, where histograms are created. You process, which is called for every event where you fill your histograms. And then finalize, which is called at the end, but you probably don't have to do anything there. So in init, you can set the output file name. I'm just going to keep it, well, I'll change it, session3a.root. Then we can scroll down and see. You can see here that we're going to be creating some histograms. So here's example histograms for missing mass squared, beam energy, some actions, etc. And then in the process, this is called for every entry in the tree. We're setting up our actions. I'll get more into that in a second. And then we loop over all the particle combinations in the event. So we set the index for those in the wrapper. And then if we scroll down a little further, here we're getting the 4 vectors, out of the wrappers for the beam, the proton, the pi plus, the pi minus, that decaying pi 0, photon 1, photon 2. It automatically looked at the metadata and figured out what particles you had, and it put these C++ wrapper objects to the tree, and it's automatically getting the P4 for you, etc. And then we're filling some example histograms. So okay, let's just see what this does when we run it. I called it session 3A. That's right. All right, so to run it, we just do this. So we launch root with the tree file. We load this library. We load this script at the beginning, which will load the library, and then we process the tree with our selector name. So let's do root with the file name. Then let's load So that load script, I went ahead and made a soft link here, so just to make it faster. And then let's process the tree. So here's our tree name. Process deselector session 3A. And the plus tells it to compile the code. It'll run faster that way. All right, so this is going to run, the default code that was in there. This prints the screen just to show you that, hopefully this is what you had in mind. Hopefully this should be what you set up in the D reaction at the beginning. Gamma P to omega proton, omega decays, pi 0 decays. If that's not what you were expecting, let me know. But it should be.
Objects like the D histogram action particle combo kinematics, where do they come from?
I will show that in a second, but that's a class that we made. It's an action class similar to what we were doing yesterday with those other action classes. Okay, so it finished. So we have a new root file, session 3A. So let's open it, see what we have. All right, so this is out of the box. I haven't changed any of the code yet, but you can see, for example, here it's histogrammed the missing mass squared automatically. And this looks worse than we had at the end of the day yesterday because there's no particle ID cuts yet, etc. Here's a histogram of the beam energy. You can see the coherent peak here at 9 GeV that we simulated. And then particle combo kinematics. So in here, we can look at the photon, P versus theta, for example. So we got a lot of photons down here, but hopefully some timing cuts will get rid of some of the background, et cetera, et cetera. And particle ID information was automatically histogrammed also. So, pi plus. Here's that delta T histogram again we were looking at the other day. For the pi plus timing and the time of flight.
This is an alternative method to do the same things we did yesterday.
Yes. So in general, running over the data in the T tree is much faster than doing it in JANA. But at the same time, you don't want to do everything. If it's something simple, you may as well do it in JANA and get it over with. And so that way your T tree is smaller and you have less combinations later. But at the same time, you don't want to cut too tight because you can always cut tighter later, right? But you can't undo it. So in JANA, we generally recommend doing loose cuts that are reasonable, and then you can do tighter cuts later, for example, in a root tree. So, but you can do things either way. It's up to you how you want to do it.
What's the rough size of your file? This is like a standard format, right?
Yes. So this was. So this particular file was 216 megabytes for how many events? Or whoops, wrong one. So 51,000 events. So 51,000 events was 200 megs, but the size depends on the number of combinations, which you can cut down a bit. But probably not, as long as the number of combinations is small, the combo-specific branch data is small. So a lot of it's just storing all the 4 vectors for all the unused cracks and neutrals and things in there in case you want that information later. So
is there a way to do that? I mean, can you tailor this without completely rewriting that?
You can add more. You can add custom branches. I didn't talk about that yesterday.
But you can't delete things.
You cannot delete things. This is the standard format. It's designed such that everything you could possibly want's in there. For example, the distance between the showers and the tracks, in case you want to do some cut on that later, that information's in there.
So this seems to me this is like a prototyping environment. You wouldn't do your final analysis on all the data like this.
What do you mean?
I mean, you can't have 26 billion events.
Well, for example, I mean, we saw that missing mass squared histogram. We could have cut that much tighter, right? The pi 0 had a huge background. We could have cut that much tighter. We could have required more than the kinematic fit converged in the first place, right? We could have put on tighter cuts, but we chose not to, just so we could show you how to do things in root. So the file is much larger than it would be otherwise.
Yeah, if you place loose particle ID cuts,
right, it would have.
The number of combos
and the number of events shrinks too.
Dramatically.
Right.
So this may be big.
This
like
is,
you said, for pedagogical reasons.
Yeah, this one's overinflated. Let's see. All right, so we made all those histograms. So let's look at the code again, a little more detail. All right, so at the beginning, we created these actions. Later, we filled them. All right, but you can see this. So like for the beam energy histogram, here we fill it with the beam P4. But first, we're doing some checks for uniqueness. So the trick here is within an event, you could have many combinations, right? So we saw sometimes we have up to 20 combinations. But some combinations might have the exact same photon for the beam between them, and you don't want to histogram that value twice. You just want to know what the distribution of the beam energy was. So you need to be careful and make sure that the value you're histogramming is unique. So let me talk about that in a bit more detail. This is really important. I've avoided talking about it so far, but if you do it wrong, you'll get the wrong yields. For example, you can double count the number of omegas you have, and this would be bad. Get wrong cross sections, etc. So double counting will happen anytime you're histogramming some quantity about a particle combination, and you get one of those, more than one of those in an event. Because hopefully one of those combinations is signal, but the rest of them are background. So you need to histogram, the mass of the omega for all combinations, because they're all, hopefully you've got some cuts that narrow it down to only one, but sometimes you'll still have 2 or 3 combinations left. So in general, this is a problem that you need to handle. So again, with that beam energy, let's say we had just 2 combos in the event, and the only difference between the combos was, one of the photons for the pi 0. Maybe there were 2 candidates for it, a real one, and then maybe some extra hadronic shower in the BCal. So we'll have 2 different combinations, but the beam photon is the same for both. So if you were to histogram the beam energy twice, you would be double counting. Does that make sense? So you'd be tricking yourself as to what that beam energy distribution should actually look like. And so you can guard against it by tracking the uniqueness of the beam ID number. So each of these particles has an ID number to help you with that. So if I look at the code again, you see right at the beginning I'm getting these indices. So this beam ID, this proton ID, this pi plus ID, pi minus ID. That helps. This will help you keep track of making sure it's unique. So for the beam energy, to track it, what I'm doing is I have this set of integers where each time I filled, the histogram, I'm going to add the ID to the set, saying, okay, for the beam, beam particle number 1, once I fill it, I put it into this set, and then I check to see later whether I filled it or not for that one. Okay, so here's the code. So if I haven't used the beam ID yet, so this is in a set, a C++ set, the way you can check to see whether something is inside it or not is you try to find it, and if you can't, if the iterator is at the end of the set, then that means it's not, that beam ID is not in the set, it's unique, so you can go ahead and fill the histogram. But then once you do that, you insert that beam ID into the set, saying you've used it. So this is a way for you to keep track, okay, I've histogrammed the beam energy for this photon, don't do it next time. So if that thing is reused in the next combo, this will return false, and you won't enter this section of the code.
Does that mean pretty much everything you histogram has to have this type of code in it?
Yes, everything that is combo dependent, because you can have multiple combos per event. If what you're histogramming is independent of your combo, then no, you don't need it. So if you just want to histogram the total energy of every shower in the BCal, that has nothing to do with your reaction, right? You can just histogram it once. But if you're histogramming, say, the mass of the omega, then yes, you need to do this kind of check.
I think it would be possible to implement some class which handles that for you, so to say, in a unique way, so that you just fill unique bit or so, and then.
So this is what the code in Jana did. It was doing that. The code for for those particle combo kinematics that we were just looking at a second ago, that does it for that also. But I haven't ported that code for the mass histograms into root yet. So you guys get to practice with it.
So I guess I didn't understand. I can understand why the beam energy you wouldn't want to fill twice.
Right.
But the omega mass, it seems to me you want to fill that twice.
So let me go into some more examples, and we'll cover mass.
One other thing, for each combo, do you have like a chi-square from the fit?
Yes. Yes.
So one nice way to handle this is you mark the best chi-square. So
Never do that.
you have.
You are biasing yourself. Whenever.
Depends on what you want to do.
Okay. Depends on what you want to do. Yes. In general.
But then you're guaranteed one entry per event, and you just plot it for the best.
Right, but you're also, in general, selecting the background that happens to be underneath your peak, and now you no longer have.
Mass constraints in your.
But then you no longer have a handle on what the shape of the background is on the sides of your
you have
peak.
to be careful when you're doing it, but that's one way to guarantee one entry per event.
Don't do it unless you know exactly what you're doing.
On practical.
That applies to anything, by the way.
Not just
in life as well.
What's that?
Practically, how sharp is the peak of the unique combination, of the right combination?
It just depends on what thing you're histogramming.
Oh, I mean the combination as a whole, so which contains, of course, the beam and the particular combination of the particles.
Right. So you mean how?
The question is, so how well typically the right combination differs from the wrong combination. For example, if we had a very good resolution in the tagger, so the other combinations will be far away. So,
Right. They might have the same time. You could have several with the same time, but probably not the same beam energy. So tagger's typically not the problem. The problem is you have background underneath your signal peaks, and so it's just going to depend. I don't know how to quantify it exactly.
So is your point that statistically, so chi-square doesn't separate them? They're perfectly fine, so like probability of 40%.
Oh, I see. The difference.
20% do not matter.
The difference in chi-square between the best one and the next best one.
Yes.
It probably varies channel by channel. I don't want to give a guess on that. You probably have to study it for your specific channel. Okay. Let's move on. Example number 2. Pi 0 invariant mass. So let's say you have many combos in your event, and some of them differ only in the tracks, like the proton or the pi plus. So in that case, you'll have the exact same mass for the pi 0 in both of those combinations, right? Because if the only difference is the proton, the two photons are the same. So you can guard against this by tracking against the uniqueness of the pair of photons that you're using to fill the pi zero. And again, some combinations differ only in photons. So one of those pi zero combinations would be signal, and the rest of them are background. Okay, let's histogram the pi zero mass now. So I'm going to create a histogram in the header file. Define your histograms here. th1i dhist pi zero mass. Okay. And then where everything else is created, I'm just going to slam it in here. Oops. Hist pi zero mass equals new I pi zero mass. Mass. Then let's do 170 bins from 50 MeV up to 220 because I think that's where I put the cuts last time. All right, copy. And then we need to fill the histogram. All right, let's just insert it here. So pi zero mass, fill. Pi zero P4 was, or no, let's take these. Damn it. Sorry. Boy, skipping farther than I expect. Here we go. Let's grab the measured floor momentum because we kinematic fit it, so it would be fixed if we did otherwise. So double pi zero mass equals photon 1 plus photon 2 dot m fill. Okay, but if we do that, we're going to double count. So we need to guard against double counting. So I'm going to create a set of sets of int t. So, so far pi zero mass. All right, so y set of set. So I have a pair of ints for each pi zero. So I use a set, keep track of one pair, and then the set of sets is the group for the each combination of the set of pairs. So this is the photons within the pair, and this is the set of all pairs. So then we go down here. So we're going to make use this combo pi zero mass. We're going to insert the ID numbers. Here's the ID number. Went too far. Insert one. Insert the other. Then we do a check just like this. So if used so far, we check to see if the one for this combo has been used yet. If not, we fill, and then we set it, and the use so far, we add it there. All right, this ought to work. Load the selector. Let's process. All right, so yes, coding that up for everything you histogram is not fun. And so hopefully we'll be getting to add more of those things soon. But if you want to know what the true distribution of the pi0 mass looks like, your signal and all of your background, this is something that you just have to do. If you pick the best one, then you will be biasing your distribution to only show, because the pi0 mass was the constraint in the fit. So if you only choose the best one, then you will be biasing your distribution. Okay, so let's look at the results. Call this session 3a.roots. Open it in the browser. pi0 mass. Okay, there it is. Yes.
But you will have to change the way you deal with that depending on what you are looking at, right?
Yes.
I mean, now you're looking at pi0 mass.
Right.
So you know you can throw the rest away. You don't want to double count them. But in other histograms, they may get affected. You may be cutting some compounds that are neat, right?
I don't understand the question.
You are just using the first combo in every event.
No. We loop over combos. We're loop over combos. So this is inside of the loop over every particle combination.
But when you get to the beam uniqueness part,
Yeah.
where you dealt with that beam, you just do the rest of the combos. That's what I understand.
Throw the rest of the combos.
You don't tell the histogram for the pi0 mass with that.
I still don't understand. The idea is you loop over every combination, and you want to know the beam energy for all of them, or the pi0 mass for all of them, and what defines, a unique value is different depend on what you're looking at. So.
Oh, I think what he's asking is if you say I've used this beam photon so far, do you stop looking at any combo that use that to get the mass that you're looking for?
No.
Was that your question, roughly?
I didn't hear exactly what you said.
If you've marked the photon that used, you stop looking at all the other combos when you look at the mass. Like, will you stop everything? Was that your question? That you just...
No, that's not the case.
Yeah, but I guess I got the second time you explained it, I guess I got it.
Right.
We have a question. In case you're doing fitting, so to say, and you're using let's say the same two tracks for reconstructed row or whatever, and let's say a pi0 besides that changes its combination, and therefore the fit gives you also a different result in the fitted 4 vectors of the row pions.
Right.
What do you do in that case? Do you reasonably? That's
tricky. In that case, you would probably you would probably pick. You want to do all unique combinations of the row, but if there are several fits for the several kinematic fits where the chi-square has changed for those, then you probably just want to pick the one with the best chi-square in that case.
Okay, matching that.
Yeah. All right. So the general rule is you want to only histogram for unique combinations of particles for the given PID. So, you could have one track be used as a proton hypothesis, or you could treat it as a pi plus hypothesis. It's used as both until you do a particle ID cut, right? But that's a unique combination, whether you use that track as a proton or pi plus. So the general rule is only histogram for unique combinations of particles with that PID. Which particles do you worry about? just the ones that were used to compute that quantity. So to test for uniqueness on the pi 0 mass, it's independent of the track, so I wasn't even looking at that. Okay, example 3, missing mass squared. So to compute missing mass squared, it uses all the particles in the combination, so it should always be unique, right? Not quite. Usually it is. And in our case it is. But suppose you were looking at this channel, our favorite B1 pi channel, where it's 2 pi omega, and then the omega decays to pi plus, pi minus, pi 0. The pions, like this pi plus and this pi plus, could be swapped. And you would, whether they were swapped or not, so if they're swapped, you would have 2 combinations, but the missing mass is the same. So just be careful when you're doing this.
That's only true before you do the kinematic fit, right?
The omega is not constrained in the kinematic fit,
I mean,
if that's what you're getting at.
But if you had a constraint, then things could be.
Even then, you want to make sure that.
But you always get the combos.
Yeah.
I mean, you've made a fit and some cuts to keep these events, but these events always have the combos. There's always 2 pi's, pi plus is always 2 pi minus.
Right, and the missing mass squared will be nearly identical, even if the kinematic fit chi-square is slightly different. Okay, all right, so that's all I want to talk about for that. As an exercise, you guys will histogram the mass for the omega. But first, I want to talk about proof for a second. So proof allows you to run multi-threaded over a T-chain, where a T-chain is a collection of trees, for example, spread out over many files. So typically, to run proof over your data, you have to, if you were just using a basic T-selector, the code that you would need to write to run just over the the tree is different than the code that you need to do in proof to run over a chain. And it's really a pain. So, but I designed the D-selector such that you don't need to change the code. It abstracts it away. You don't have to worry about it. But proof itself is designed for distributed computing across many nodes, and that's beyond the scope of this workshop. But proof light is similar to proof, but it's not distributed computing. You could run multi-threaded just on a single machine. Again, this is kind of a pain to set up because you have to package libraries, etc. But the code that I have already does it for you. There's instructions here. And so there's only one core. There's only one virtual core on the virtual machine. So you really shouldn't be doing it here because it'll actually go slower. But I'm going to go ahead and demonstrate it here just to show you. So follow the instructions in the browser here. Let's see. So if I open Firefox, I can close this. Open Firefox. We have a link. We have a bookmark to, here's the deselector documentation. I scroll down to the end, and it tells me how to do it with ProofLight. Everything is already built, so all we need to do is run. So let's get to the terminal. So root -l, load the selector, and then there's this ProofLight Manager class, which does everything under the hood that you need to do to run proof. So first argument is the tree file. So paste that. Why are you not copying? All right, forget it. I'll just type it directly. Right. Capital. There we go. There. Found it. Change. All right, name of the file. Then the second argument was the name of the tree. So scroll back up. That was here. The next argument is the name of the selector. So dSelector session 3A plus to tell it to compile. Then the name of the output file. Call it 3A proof.root. Then the number of threads. So we only have one core, so I'm just going to do 2 threads. So this pops up a GUI. You can run root with -B and it won't pop up the GUI, but this shows you how it's doing. And then if you want to look at the logs, that'll show you the cout messages from what's running. All right, it's done. So then if I look, I've got a new file, 3a.proof. And it's got all of our histograms again. Beam energy, pi0 mass, etc. So that's how you can run multi-threaded on your, on your own local machine. But beware, unlike JANA, histograms are duplicated. So in other words, for each thread, there is a new histogram object. So, I mean, that's good in some ways because you don't need blocks to fill the histograms. But it's bad because it'll blow up the memory usage on your computer pretty quickly. If you're running with 10 threads, you've got 10 copies of each histogram, and it blows up. So just keep that in mind. And also, please don't abuse the JLab farm machines because there's limited RAM and CPU, and nobody else will be able to do anything. If you just run 10 cores, fill all your histograms there. But that's it for this talk. So the idea is dSelector, you can use that to run over the tree, and it makes life simple. It gives you the 4 vectors, for the momentum. All you need to do is play with them and fill histograms. You need to beware double counting, or else you'll get yields wrong. So you need to check for uniqueness for each quantity that you histogram. And let me emphasize, do not take shortcuts on this, unless you know exactly what you're doing. Prooflight lets you run multi-threaded, no change to the code needed. And then there's some exercises. We don't have much time right now, but for example, one of the exercises is the histogram, the omega mass. And you can use the missing mass, the code that histogram the missing mass and check the uniqueness. You can use that as an example. And so we'll see Justin's talk next for more on event selection for our channel. Does anybody have any questions? All right, so we've got 10 minutes until Justin's talk. So why don't you guys, take a look at the README, see if you can histogram an omega. First, just see if you can histogram it, and then see if you can figure out how to check for the double counting correctly.
There's difference between the output files after you did the make selector yesterday and the one that I had. Have you done any editing to make selector?
I'm sure we have.
Okay.
We've been.
Would it be like a huge difference in the outcome files? Because one of the things was like the first thing that came up in one of the files is it talked about some thing, and in a header file or something that I'm getting a run number.
I don't remember exactly. We were making a lot of tweaks to make sure things went smooth for the workshop and add things in. I can't tell you exactly what the difference was. Chances, the results of your analysis won't change, but maybe some things will be more convenient. I would update anyway, and then probably most of your code you can just copy paste.
Is it something that I would have to get pulled?
Yeah.
Okay, that's why. 'Cause I only use the arbitrary one.
Yeah, I would get pull, rebuild, and then just copy paste your specific code into a new one, and then it should be fine. I doubt we'll be changing it too much more in the future.
Okay.
Yes.
Where is the bin ID? Where is the bin ID defined?
So it's a branch in the tree. There's a branch in the tree. In the tree itself, it's just a unique number.
Who
0,
fill
1.
it? How you fill it?
When I filled the tree in the first place, Jana fills it. Jana fills it.
If you have several photons in the bank, right?
Right.
How are you choose?
So not all of them are saved. Only the ones that survive the cuts in your combinations are saved. So when we cut on the timing of the photon and the missing mass squared, that narrowed it down quite a bit. So we were only saving 1, 2, 3
Right.
photons.
Suppose you have two.
Right.
So the bin ID.
This ID is just one of them will be labeled number 1, one of them will be labeled number 2. It's just
So
it's
1
just
and
a
2
label.
you have.
Yeah.
Okay.
Or 0 and 1.
So you can have more than one ID for each of them. That's what.
Yeah, each unique photon in there will have a unique ID number, and it's just
So
for
each
bookkeeping.
event, right?
Yeah,
You
for
have
each
1
event.
and 2, for example.
Yeah, for 0, 1. Yeah, 0, 1, 2,
It starts
0.
0, 1.
Yeah.
And the other thing, I don't understand this. Why you get duplicated as the last thing? Duplicated in the multi-threaded.
So proof is designed to be distributed computing. So on each node you'll need histograms. Histograms on this.
Independent, so you
Right.
don't collect it.
Right, and then you collect it at the end. It's collected at the end of proof. Histograms are merged together at the end.
So each are independent.
They're independently
And then they
filled
collect.
and then merged. Yes.
Okay.
Right.
There are multiple, but they are all different.
They are in separate spots in memory.
Different events.
Each thread has its own. The content of each is different, and then it's merged together at the end.
Oh, okay. All right. So they are not duplicated. They are not the same.
They are not the same.
Okay.
Because each thread's doing half the events, right?
Okay. Yeah. No, if you have. Okay.
And just remember, there's solutions also to the exercises. There's solutions there too.
So I had a question.
Yeah.
The non-double counting checks on the photons. Say you had an additional combination in the event where the vertex shifted.
So if the vertex would shift for a reason, because one of the particles is different. So I see. So you're saying.
So the invariant mass of the pineapples shift because the vertex is shifted.
Yes, that's right. The most important thing is that you get the yield correct. So as far as how you deal with combinations, the yield must turn out correct. So depending on which vertex you pick, the floor momentum will be slightly different, and the pi zero mass distribution will be slightly different. So you have to pick something. So I recommend, picking the one with the best confidence level in the kinematic fit.
Okay.
To be most likely correct. But I don't.
I doubt it'll shift far enough.
Right. I don't see a way around it.
Yeah.
My built-in stuff just picks one. It doesn't. But yeah, it's not pretty, right?
Yeah. It's something you have to be careful,
cognizant of.
Yeah.
It's better to be overly cautious than to just start doing stuff.
Yeah. You will get the yield wrong. You will get the background wrong if you just pick the best one. you'll have no idea what the yield is because you don't know what the background is if you just pick the best one. Because you're inflating your peak by picking the peaking background. Okay, you need to set up. Do you want to use this or not? I found it's convenient in case the Wi-Fi is not so great.
Maybe useful, yeah. Oh, I don't have my dongle. That's okay.
Okay. You want to use my charger since it's, well, I probably need my charger.
I have a different. I think they changed the form factor for the plugs. Oh, I can use that one though.